Good day, class. In this recording, we will look into the second application of integral calculus. That is the computation of the volume of solid of revolution. When we say solid of revolution, these are solids that are created by revolving a certain plane region about a certain axis. One common types of solid of revolutions are the sphere, which is a solid created by revolving a semicircle about its diameter. We have the cylinder, that is a solid created by revolving a rectangle about one of its sides. And finally, we have a cone wherein we revolve or rotate the triangle or a right triangle about one of its legs. Now, our task is to calculate the volume of different solid of revolution wherein their formula is not predetermined, unlike the aforementioned solid of revolutions. So now, imagine if the region bounded by y is equal to f of x, x equals a and x is equal to b. So practically, this is similar to the region we have discussed in the previous application. But this time, we will rotate this region about the x-axis. So if we would rotate that about the x-axis, the resulting solid is called the solid of revolution. So this is going to be that particular solid. Now, to calculate the volume of the solid, we will subdivide or slice the solid into a very thin shapes. So imagine from this shape, we slice one particular part of it. So consider one very thin slice perpendicular to the axis of rotation. Now, as we can see, the dimensions of this particular solid is that y would be representing its radius, and then the thickness here, which is very thin, similar to the concept that was introduced in the previous application, this is going to be our differential in x, which represents the thickness. The very thin slice is in the shape of a thin cylinder or disc. Now, recall the volume of a cylinder to be equal to pi r squared h, where r is the radius and h is the thickness or the height. Now, from the considered slice, we can easily correspond these dimensions with the measurements in the Cartesian coordinate system. For example, r is going to be the y dimension, and h is going to be the dx dimension. So therefore, the volume of this thin slice is going to be a differential of the volume because of the very small thickness. Its volume will be also very small. It is going to be pi y squared times dx. That is just following the formula of a disc. That is r representing y and h representing dx. Now, since the total volume or since we want to calculate the total volume, we can do that by summing up the volume of these disks. And in this context, when we say summing up, we mean integration. So we integrate from lower limit a to upper limit b of pi y squared dx. So this method is called the disk method. Now, there are three methods that we will consider and discuss. These methods only differ in the different shapes of the solid of revolution created by a rectangular element. Now, the shape of the strip may also be realized by considering a rectangular element and visualizing what solid will form once rotated. So for example, since we want to rotate this area or this region, let's consider first our chosen orientation of rectangular element. Let's say it is going to be a vertical element. And let's say we want to rotate that about the x-axis. So by realizing what the shape is going to be, we can see that if you rotate that particular rectangular strip, it will create sort of a thin cylinder or disc. So therefore, that is one way of visualizing what will be the method to be applied. Now, consider this region bounded by the two functions, and again, it is going to be rotated about the x-axis. And let's say we considered this rectangular element as our representation of the area. Now, to represent the volume, we have to imagine what will happen to that representative element when we rotate it about the x-axis. So if you rotate that, it will form this particular solid. Now, this particular solid is called a washer, and we can recall the volume of a washer that is represented by the following dimensions: the inner radius and the outer radius and the height or the thickness. So therefore, the volume of that is going to be the volume of the area of this annular region, which is going to be the area of the bigger circle minus the area of the smaller circle, and simplified in this way: pi outer r squared minus inner r squared times the height or the thickness. Now, from the considered slice in our example here, we can see that the height is going to be represented by dx, or the thickness is going to be represented by dx. The inner radius is going to be represented by y1, while the outer radius is going to be represented by y2. So therefore, following the formula for the volume of a washer, we can say that the differential volume of the solid of revolution is going to be pi times y outer squared minus y inner squared times dx. Again, if we want the total volume, all we have to do is to sum these washers or integrate. So the limits will be the points of intersection of the region. And since we are integrating with respect to x, the limits should be x coordinates. So, by the way, this is called washer method, simply because the created solid of revolution from the rectangular strip forms a washer shape. Now, let's consider the same curve, but this time it is going to be rotated about the y-axis. Now, we can assume that our representative element will still be vertical. And like what we did in the previous two methods, we will just imagine what will happen to that particular element once rotated about y-axis. Now, it has created this particular solid. Now, don't be mistaken. This solid is not a solid cylinder, but rather it is a thin-walled cylinder. So imagine a can of a tuna or a can of corned beef. No? So we are not talking about the inside of the can, but rather we are only talking about the metal or the aluminum can itself. So now let's recall the volume of a cylindrical element. So in order for us to calculate the volume of a can, we need the mean radius, the thickness of the cylindrical shell, and the height. So the volume of that is going to be 2 pi RH times thickness. So the term here, 2 pi R, represents the circumference. And then the thickness, multiply that with the thickness, that is going to represent the area of the base or the upper portion of that particular shell. And then if you multiply that by height, that is going to give you the volume. So this is the formula to be recalled. Now, from the given drawing from the considered shell, we can say that the thickness is going to be equal to dx. And then from the dimension of the rectangular strip, which has a height of y2 minus y1, that is going to be also the height of the cylindrical shell. And then the distance from the origin or from the x-axis to the rectangular element considered, we can designate that as the coordinate x. So we can say that the mean radius is equal to x. So therefore, substituting all of this from the general formula of the volume of a cylindrical shell, we have the following equation. 2 pi x representing the radius, y2 minus y1 representing the height, and dx representing the thickness. The total volume can now again be calculated by integration. Again, note that we are integrating with respect to x, thus the limits should be in terms of the x coordinate. That is from this point up to this point, which is the boundary of the regions. So this is called the shell method or the cylindrical shell method. In summary, you just need to recognize and draw the curves first. And then secondly, choose the orientation of the rectangular element and visualize the solid of revolution form. There are only three possibilities. It could either be disc or washer or cylindrical shell. And then apply the relevant volume formula and define each parameter from the graph. Define the limits of integration such that given boundaries and or point of intersection. Apply integration to evaluate the total volume. Let's have an example. Example number 1, calculate the volume of solid obtained by rotating the region bounded by y is equal to 2 square root of x minus 1, x-axis, and x is equal to 5 about x-axis. So to visualize this region, we will need to draw all of this curve. And we should apply our knowledge in analytic geometry or pre-calculus in graphing these particular curves. So now this is the graph of the first curve. This is the graph of x is equal to 5, and this is the x-axis. So therefore, the region being considered is this particular part. So we will be revolving about the x-axis. Now, let's choose a rectangular element. So let's say we choose a vertical element. Now, we will imagine what is the type of solid of revolution form. And it seems like that is a disk. So let's define the dimension of this disk. The thickness is going to be dx, while the height is going, or the radius, I should say, is equal to y. The solid form is a disk, so this method will apply. So recall the formula of disk. Volume is equal to pi r squared h. Now, if we would correspond that with all of the dimensions in the graph, we have the differential volume is going to be equal to pi y squared dx. And then also, the limits would be from x is equal to 1 to x is equal to 5. So you might be thinking, how did we end up with x is equal to 1? So from the drawing, this curve is actually representing a half parabola. So all we have to do is to determine the vertex of this parabola by converting it to its standard form, like what we did in the previous application. And then we would be able to figure out that this is the point where it would intersect the x-axis. Another way of doing that is by setting y to 0, because we want the point of intersection of this curve with the x-axis. And in x-axis, all values of y is 0. The upper limit is self-explanatory. As we can see, it is just the right-hand boundary of this particular region. Now, applying the integral of from 1 to 5 of pi y squared dx. So of course, since we are integrating with respect to x, we must replace y in terms of x. As we all know, that y is represented by this equation. Thus, we can replace that by 2 square root of x minus 1. We can expand, or we can evaluate the exponent first prior to integrating. And in this case, we did that exactly. And then, as we can see as well, this is an easy function to integrate. So let's just apply power rule, and then apply or insert the upper and the lower limit, and that would give us the volume of the solid. Let's have another example. Determine the volume of the solid obtained by rotating the region bounded by y is equal to 2 square root of x minus 1, x-axis and y is equal to x minus 1 about the y-axis. First, we need to graph all of the given curves. And this is the graph of those curves. So this is the same curve as the previous example, and then we just added another line, which is y is equal to x minus 1. And we will revolve this about the y-axis. Now, we are free to choose our orientation here. Actually, you can use either vertical, rectangular element, or horizontal. Both are applicable. Now, I have chosen a horizontal rectangular element. And then since we would revolve this about the y-axis, let's imagine what will happen to that element once revolved about the y-axis. It will create a washer. So let's define the dimensions. That is the inner radius represented by x1. Outer radius is represented by x2. And the thickness is represented by dy. So washer method will apply. So recall the formula of the washer. Volume equals pi r2 squared minus r1 squared times h. So therefore, from the given graph, we have dv equals pi x2 squared minus x1 squared times dy. Now, in order for us to integrate this, we must find the limits which is represented of the y coordinate because we are integrating with respect to y. So let's define the limit. So let's find the point of intersection between this line and this parabola by algebraic method. So we can equate both y and then we can expand by squaring both sides. Expanding the left side, you have x squared minus 2x plus 1. Distributing 4 to x minus 1, we have 4x minus 4. And then transposing everything on the left side of the equation and then equate that to 0, we create this quadratic equation. And using quadratic formula, we can solve for x. That is x equals 1 and x equals 5. So those are the point of intersection of this curve, or should I say the x coordinate of the point of intersection. But since we mentioned that we need the y values, so all we have to do is to substitute this x in either of these two equations to solve for their corresponding y coordinates. So in my case, I just use the equation of the line because it is simpler. However, we can also choose to use the equation of the parabola if we want to. Anyway, we have y when x is equal to 1, y is equal to 1 minus 1, and that gives us 0. When x is equal to 5, we substitute the same thing and we get y is equal to 4. So therefore, those are the lower and the upper limit in y coordinates of those two curves. Now, recalling that the volume can be calculated as the integral of pi x2 squared minus x1 squared dy, finally, prior to our integration process, we will need to replace all of the variables x2 and x1 by in terms of y because we are integrating with respect to y. So note that x1 is represented by this curve, the pink curve, and that is represented by the parabolic curve. So x1 will be this particular x. So from the given equation of the parabola, we just need to algebraically isolate x. So what we did here is we can square both sides of the equation, transpose 1 on the left-hand side, and then divide by 2 squared, which is 4. So we get this particular equation. So that is your representation for x1. Next, for x2, it is bounded or represented by this line. So all we have to do is just use the equation of the line to solve for x2. That is y plus 1. And then substitute that to our integral. So from here, we can now apply the integration. It's either we can expand everything first. So in this case, it is necessary to expand. So once expanded, you can now integrate. So I have skipped showing that particular solution because that part we should all already know at this stage. So this is now the antiderivative, and then substituting the upper and the lower limit, that gives us 208 over 15 times pi. And that would be the volume of the solid generated. Now let's consider example number 3. For example number 3, we will consider the same region. However, we will revolve that region this time about the x-axis. So again, graph, and then choose a rectangular element. So let's say I still chose a horizontal element, although it is also possible to use a vertical element for this particular problem. And then let's visualize what will happen once revolve about the x-axis. So it will generate that particular solid. And that particular solid is a thin-walled cylinder or cylindrical shell. Let's define the dimensions. So the y here would represent the radius. dy would represent the thickness, and the height would be represented by the difference of x2 and x1. So recall the volume of cylindrical shell, that is V equals 2 pi RH times thickness. So therefore, dV is equal to 2 pi. The radius is represented by y. The height is represented by x2 minus x1, and the thickness is represented by dy. Since the integral is with respect to y, limits will be in terms of y. Actually, the limits were already defined in the previous example, but we can just simply repeat that process here to show how it is done. We solve for x, and then we substitute the values of x in the equation of the line to solve for the corresponding y. So those are still our limits. Now, evaluating the integral first, let's substitute all of the values of x. So x1 is represented again by y squared over 4 plus 1. And x2 is represented by y plus 1. So therefore, substituting that to our integrand, we have the following. So again, you can expand and integrate. So, and then we will have this particular expression. So substitute the upper and the lower limit, and that is going to give us the volume of the solid of revolution.